Oops. So, welcome to lecture 7. And so today we're gonna really dig into the series expansions. First starting with the high temperature series expansion. And we're going to look at this by working it out for an example, namely the 2D zero field Ising model. So we have a Hamiltonian with the interaction coupling with sum over nearest neighbors as I as J. I know a flat field. And now here's a mathematical trick. And so yay, celebrate, right? 1D was kind of boring, no phase transitions. We're really talking about learning about two-dimensional models embedded in 2 dimensions, hoping that we are above the lower critical dimension and hence will see phase transitions. And so the mathematical trick is now to see that because it's the Ising model, so this product of Si Sj can only take values plus or minus 1. I can rewrite the Boltzmann factor Si Sj as e to the beta j plus e to the minus beta j half plus Si Sj e to the beta j minus e to the minus beta j over 2. So what's the idea? We can check. So at Si Sj equal 1, right? If Si Sj is equal 1, we would expect this factor to be e to the beta j, right? And so if we do this, so Si Sj is equal 1 here, then these two terms cancel, and I have e to the beta j halves plus e to the beta j halves. That's e to the beta j. And similarly, at Si Sj equal minus 1, I would expect e to the minus beta j, and that comes out because then if that's the case, this prefactor is changing to a minus 1. So these terms cancel out, and I'm summing e to the minus beta j halves with e to the minus beta j halves. So that's an equivalent writing. And that's the trick, because now I can, using this, I can write this. I mean, this first term is nothing else than the hyperbolic cosine of beta j plus Si Sj and the hyperbolic sine beta j, right? This is exactly the definitions of the hyperbolic functions. And now I'm gonna define this as cos h beta j of 1 plus Si Sj times V, and V is a new variable that I'm introducing here, and that's my high temperature expansion variable. So for now, I just defined and haven't motivated that this V would, so what I do is I pull out the cos, sine divided by cos gives me tang. So this is hyperbolic tangents of beta j. And I call this our high temperature expansion variable. And so why is this a high temperature expansion variable? So if we send t to infinity, which means I send beta to zero, this implies that my v becomes 0, right? So at high temperatures, my v is small, and I can, our aim will now be to show that we can write the partition function as an expansion in orders of v being recovering the result of the of infinite temperatures for v equals 0, and then looking at how corrections, if we go up in higher orders of we would change our partition function. And so our partition function if we just write it down for an Ising model, we're summing over all states e to the beta j, sorry, and then we're summing over ij si sj, and so that's, I can rewrite the sum in the exponent as still summing over all states as a product over e to the beta j si sj. And now here for this, I can now plug this in. So we arrive at, we have a prefactor cos h beta j, that we're taking the product of, like we're taking of the number of interactions between I and j that we would be summing over, right? So the number of times that I'm multiplying this prefactor with each other, with itself, is just to the power of the number of bonds, right? Because that's what we're doing. We're just summing over the number of bonds here. So if I now define curly b as the number of bonds, then this prefactor up here becomes just a cos bj to the power of the number of bonds. And then I still need to sum over the terms that have an explicit dependence on the sites si and sj. So I'm left with states product of 1 plus si sj. Right? And now what I'm going to say is, okay, look, so I'm obviously taking products of 1 plus si sj times v. Yes, go ahead.
So why would we still use the sum in front of the question?
We're summing over all states.
But we already have.
No, it's just a bracket. Yeah, it's not a sigma, it's a bracket.
Oh, sorry for that. Okay, yes, no, this is confusing notation, but this is meant to be this, and then it's much easier. Yeah, sorry for that. No, there's no sum there. Yeah, nicely spotted. But this one's still in place. Yeah, good. Okay, so we're taking products of these terms, right? So I have 1 plus si sj times v times 1 plus sm sn v times so on. And so if I start just collecting terms in orders of v, then I can see that since v is small, I can have a series expansion in terms of v. And so let's just try to start writing down a few terms in this expansion in orders of v to the n. So what we get okay, page. And so summing one of my states, but now we're expanding this product. And so we get 1 and then plus V ij si sj plus V squared, and then V squared, I have ij and m and n, or k and l, si, sj, sk, sl, and so on, right? I get, for every V, I get a pair of si, sj. And now I can identify, so what this means is that si, sj actually corresponds to a single bond in my lattice, right? It's these two neighbors that we're summing over, looking at. So this corresponds single bond on the lattice. Joining sides I and j, and correspondingly si, sj, sk, sl is then 2 bonds on the lattice, and they may be together or apart, right? I'm just taking the product, like looking at states of where I now have 2 bonds. So that corresponds to 2 bonds. A touch on. And so now just to, visualize what kind of configurations I might have over the bonds that, we be summing over, I can actually graphically enumerate these potential terms that are popping up. So I can do a graphical mapping. Derivation. Partition function. And so I haven't specified the 2D Ising model. 2D Ising model, and we're taking the square lattice as so we're going to look at graphs on the square lattice. Okay, so let's start easy. Like, what's the v to the power of 1 term? I have a lattice, and then a bond would be like this. I'm connecting si and sj. Okay, and so if I look at now v2, I can have 2 different topological representations. Let me make my 2 a little more legible. There we go. So I can have, I stick with my I and j, and now I can have k and l over here, or I can have them touch. J, and say have just L here. And you can see that really the complexity of what kind of situations I can generate on the lattice grows with the power of v. So for example, if we take v to the power of 4, then we have 4 bonds. And so for example, these 4 bonds, they can now form a square on the lattice, right? where I have one bond going from I to J, one from J to L, from L to K, and from K to I again. Let me just write down the terms for this too. So this is SI, SJ. This would be SI, SJ, SK, SL. And here I have, I'm summing over the lattice state of, say, SK is equivalent to the one of SJ, right? So what this actually is SI, SJ squared SL. And here we have them all squared, right? We have SI squared, SJ squared, SK squared, SL squared. Because in principle, I would have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 individual spins, but since I co-localize them, that they form a square, each single individual is being squared. Questions regarding this mapping? Because that's not the basis to actually evaluate these terms in the expansion. No? Okay. Let's just draw a few more. And to appreciate that the complexity of these structures that can form increases rapidly with n. So for example, if I consider b to the 8, I have 8 bonds that I could put down, for example, as 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8. Right? The space of arrangements of in which I could put down these bonds really increases rapidly. And to just write down A, J, K, L, M, N, O, then the corresponding spin enumeration would be SI squared, SJ squared, SK squared, SL to the power 3, SM to the power, oh, sorry, J was also 3. There we go. M, SN squared, SO to the power 1. And here, I, J, M, N, P, Q. I would have SI squared, SJ squared, SL squared, SM to the power 4, SN squared, SQ squared, SP squared. Okay. So we see there's going to be tons of graphs that we could put down. But here we're lucky in a sense that not all of these graphs actually contribute a value to our partition sum. And this is kind of what saves us. It's still tedious if you want to go to higher order, but we'll see. So however many graphs, they only contribute 0 to the partition function. And so how can we see this? Well, if you go back to our partition function, what we have here is a sum over the different states of SI, SJ. So for each single bond, I have to sum over all possible states of these spins. And so we have, so for example, I can have both SI and SJ equal -1, then I get a plus. I can have SI 1, but SJ -1, I get a minus. I can have SI -1, but SJ +1, and another minus. And I can have both of them being +1, and I get a plus, right? But if I take the sum over all of these states, I get 1 minus 1 minus 1 plus 1, which is equal to 0. So this is, so we found the first term, the linear term in V, actually only contributes, like the single bond only contributes 0 to the partition function. So we can happily ignore it. But we already learned, like, what does it actually need to have a positive contribution, right? A non-zero contribution. And so we see that this is only possible if we have an even exponent to one of the spins, to all of the spins, actually. So if the spins have a positive, an even numbered exponent, then I have, if I have Si to the power of 2, then I have -1. Even if they take the value of -1, I get a 1. So I'm only summing over once, and I get finite values. So only even exponents from Si avoid -1 cancellation. So terms that contribute are, if I'm summing over the states, are Si to the power of Ni, Sj, Nj, K, Nk, and so on. If they're all positive, and if they're all positive even, if they all at even even exponents, then I have for each spin taking value plus and -1, I have 2 configurations, right? And then that's true for all of them. So I get, in the end, the amount of terms that I get here is then 2 to the power of n, with n being the number of spins that I'm summing over. So this gives me 2 to the n. If all Ni are even, and this gives me 0 else. And I'm summing over n different states. And so now we can go back to our graphs and say, like, okay, so where did we actually get that the exponents are even numbers? So for sure, this was the example that we did. Like here, no, that doesn't work, right? Here, if you go to the even bonds, you know, it's all exponents of 1, so that doesn't work. Here is where we get 1 even exponent, but the other 2 are to the power of 1, so it still doesn't work. Here, we all of a sudden we had, we had all of the spins having power of 2. And so if you look at it, so the graph that we form is a loop. So this one worked. And if you keep going to the higher complexity graphs that I drew, here we have lots of even, uneven ones. So that doesn't work. And here again, we now have these 2 loops that are connected in the middle, but since they're touching, I get another even exponent, this Sm to the 4, and so this one would also work. And so we learned that those graphs actually contribute where I have loops. So to get these even numbers, I'm looking for graphs that are closed loops. And so now what I'm left with is, because I only want to look at the non-zero terms contributing to my partitions function, so I need to enumerate the closed loops that I can put on a square lattice. Okay. So again, if we go back, like the first loop that we found was at v to the 4, and you may likely see that I left out v to the 3, but obviously having 3 bonds on a square lattice, I can't form a loop anyway. So that's the first loop that we found. So v to the 4, we get a loop, and now we have to figure out like how many of these loops can we get on a square lattice. And so if n enumerates the number of lattice sides that I have, sorry, I think I haven't given this, n number of lattice sides, then I can start my loop at all, like I can hinge it to all lattice points. So I have n different ways of how to put down a square. So of this term, this one I have n times. Okay, so where would we expect the next closed loop to be found? Obviously not for uneven v's, only for the even ones. So let's try v to the 6. And indeed, the loop I can form with 6 bonds is this one. And of this, I can put down 2 n times, because now I have an orientation, I can put them that way or that one. And note now, if I want to go to the v to 7, so I get a 7th point bond, I'm kind of tempted to say, like, look, I could, I could do a bond here, right? Wouldn't that work? That's a loop too, no? But be careful, because then if I were to put down a bond here, I would generate two lattice sides with to the power of 3 spins. So I would run into odd powers again. So v7 doesn't work. And so v8, what I need to do, what I can do is I can have two loops, each build of 4 bonds. That's total makes 8 bonds, but they're not touching. Or I can have this setting 1, 2, 3, 4, 5, 6. Well, 1, 2, 3, 4, 5, 6, 7, 8. So a long closed loop. Or I can actually start to deform this loop on my square lattice. I can 1, 2, 3, 4, 5, 6, 7, 8. Or I can even make a big square. One, 2, 3, 4, 5, 6, 7, 8. You see that really rapidly, if I go up in the powers of v from 4 to 6 to 8, the number of possibilities of how I can find closed loops grows rapidly, right? So I'm stopping here, but I believe Yeomans shows you even the v10 and v12 terms, which I don't have the patience to draw you. I think you get the gist here. We still need the information of how many times we have individual configurations. I'm just going to jot this down. So this would be n times n minus 5 over 2. Of those again have 2n, 4n, and n. And so now we can actually go back to our partition function, and we can really do the summation over the states, because we know how many times we have these individual states, and we know what they contribute. Oops, what they contribute. So then the partition function still has this Washington number of bonds. Then each term contributes to the power of n. It's not sure if I was clear here. So so the loops contribute a positive value, but I'm summing over all states of the lattice. And since all the other ones, all the other spins in the lattice come in with the power of 0, they also contribute 1, right? So summing over all states, here means that I'm summing over all spin configuration across the entire lattice, and the lattice has n lattice sides, and that gives me the 2 to the n. So that I pull out front, and then our sum had a 1. That was the one from the high temperature limit. That's this one, right? Oops. That's this one. And now we're looking at these terms. Obviously, this one is 0 and this one is 0. We're looking at the v to the 4 and so on. V to the 4. We found that we have these different configurations n times. So we get plus n v to the 4. And then v to the 6, we have 2n times these closed loops v to the 6. And then for v to the 8, it becomes more, I need to sum over all these different states. So if I sum 2n plus 4n makes 6n plus n is 7n, 7n plus n times n minus 5 over 2 actually gives n times n plus 9 over 2 v to the 8. And without having drawn them, I will also give you higher order terms, 2n, n plus 6, v to the 10th, and omit even higher order terms of v to the 12th. Yay, success. Right.
One question about this, because it seems like that with higher powers of v, we also get higher powers of n. So if we were now to take the thermodynamic limit, why does this this series expansion still work?
Yeah.
N to infinity, because then it seems like higher orders contribute more.
So that's a good point. That's actually it won't. So it won't go up in orders of n, and that's a key point why this method works. And we will provide extra information. It's like it's on the next half slides of my notes, half page on my notes. So indeed, so that's why like I was lazy in drawing these all these beautiful loops that you get for the power v to the 10. But the reason that this terms is actually here in the expansion, because you see that this is still linear in n. And why is it linear in n squared? So why is it linear in n squared and not going up to n to the power of 3 and so on? Is that we're on a square lattice, and so we're just counting like how many times we can have a specific loop, and it's always max. It's always going to be just linear in how many times I can contribute them. So it won't come. And it's actually it has to drop out. So it can't go higher. And so the knowledge of that can't go higher actually helps to identify terms that can actually pop up, because I know that this is physically impossible. And I can obviously still enumerate all these loops for lower orders, but if I want to go for higher orders, it's actually useful to keep to have this information, because it constrains the number of terms that I even start looking at, right? The similar fashion of how we constrained ourselves to only look at closed loops. So yay, we have a partition function. And so if you have a partition function, we can calculate our free energy and look at all what's going on. So our free energy is minus kBT ln z. And to do that, I want to simplify this briefly so that we see this quotient dependence on n. We here have this cosine, hyperbolic cosine term. And so I'm gonna write the cosine as 1/1 minus the tangents hyperbolicals beta j. Why am I doing this? Well, because this is exactly how I defined my expansion variable. So that's v squared. And I also know for a square lattice, that the number of bonds is 2 times n. And so then I can, I have my v dependence here as well. And then I can take the full expression, and note I have this stupid nonlinear dependence of square root over 1/1 minus v squared up front. So it's actually instructive to calculate the free energy, but then actually expand in terms of v being small yet again. Small. And we get into v squared. Okay. Ooh, and this is the point where we're relieved, right? Why are we relieved? Because in the expansion, all terms with this n squared dependence, with a higher order dependence, dropped out. And so we only have a linear scaling of the free energy for the number of bonds. So the free energy per spin, so which means normalizing the free energy by the number of lattice sides, and is independent of the size of the lattice. And that needs to be that way. Like otherwise, we totally would have screwed up, because the free energy can't depend if I only have next nearest neighbor interaction on the size of the lattice. So we have all terms squared drop out. In fact, all orders. To be And so using this physical insight allows for calculating rules for these graphs at higher order. So the key is we have the free energy, and now from the free energy, we can actually derive the thermodynamic properties. Before we dig into this, before we actually going to look eventually at the specifics of the Ising model, we have to note that the success of being able to do this high order, high temperature series expansion really relies on us doing this trick of rewriting. So it all boils down to, sorry, I'm going to scroll back down. This, right, that we are able to rewrite the Boltzmann factor in terms of a prefactor, and then we have this relationship. So that's key. That's why it works for the Ising model, and cannot necessarily be generalized. Although I'm gonna just go into how we can generalize this concept. So. Which is a unique of the Ising model. Okay, so how can we generalize? That's the next point. So the generalization of the high temperature expansion. So let me write down just a general form of a partition function, which is, you know, summing over all the states. I have e to the beta of an Hamiltonian. And so what I can do is I can also write down expansion in terms of evaluating the traces of the powers of the Hamiltonian. So I'm expanding the exponential function actually. So I can, if I expand this exponential functions, I can also write this as 1 minus beta h, sorry, h, oh well, plus beta squared h squared over 2 faculty, and so on. So, and what this means here is now here I need to evaluate traces of powers and again, mapping on graphs helps. And here really the challenge is, you know, how you can you become good at, like, you know, figuring out which graphs and enumerating the amount of graphs. So it's really an art. You know, how to find rules to speed up counting graphs. So it sounds very tedious, yet it is in fact widely applied. And so if I then also want to calculate the free energy, we already see, get a hint at the next chapter opening up eventually. So the free energy per spin would be ln z over n times beta. But the way I can enumerate this now is to look at the at these individual terms and evaluate these Hamiltonians looking at the case of no interactions. So it will make more sense when we when I start showing you mean field theory approach, but just so that you see that this is actually consistent and might make more sense later on. But let me just show you that these terms and so on. This in principle also follows from the generalization of the high temperature expansion, where these averages are calculated over non-interacting spins as outlook. Okay, so that was the high energy, high temperature series expansion. And so now we're going to look into the low temperature series expansion, and then we're going to see what we can learn about it specifically for the Ising model. Yes.
So in theory, we should be able to apply this generalized formula to the Ising model also, and we should get the same high T expansion. But like, I don't see how we could get tangents hyperbolicus terms from.
Yeah, we wouldn't get tangents hyperbolicus terms, but we would like the no, so like you actually, so in lowest order in the Ising model, and no, I'm sorry, in lowest order in mean field theory, we do because we evaluate the Hamiltonian at the non-interacting state, we do get you do arrive at tangents, the tangents hyperbolicus will pop up again. So what we can do once we actually solved it this way, which we're going to do in mean field theory, which I believe is coming up next, but I think it's not next Tuesday just yet. Oh no, we may start next Tuesday, right? Depending on how fast I'm with the duality concept, which is beginning next Tuesday. But next week's going to be mean field theory, and then we can sort of loop back and look at and compare eventually the free energy that we find here with this free energy. And we can play the same game if we then eventually use field theories where we, so we, in a sense, we're going to recalculate the free energy of the Ising model with various approaches, and we're going to check consistency that, you know, we arrive at the same terms. This is one way, and this is just an outlook that these two are actually connected. Yeah, so, but, okay, so that was the high temperature series expansion, and now we go to the low temperature series expansion. Okay, and so the idea is with the high temperature series expansion, where we're definitely above any critical temperature, and with the low temperature series expansion, we start at 0 temperature, and we see, you know, what is the behavior below a low, a potential critical behavior, and then see what make statements at what may happen at criticality, sort of like approximating it from both ends. Okay, so here we want to find behavior below the critical temperature. And as example, we take again, oops, the 2D square lattice as a model. And we know the dynamics at 0 temperature, namely all SI are +1 as for a ferromagnet, or equally -1. And so let's think about them being in a +1 state, and what now happens if I increase the temperature from 0? What might happen? I allow for fluctuations, and the fluctuations will result in spin flips, right? And so what we're basically now enumerating is like, what is the impact of spin flips and their geometry and drawings on lattices on the partition function. So now low energy result in spin flips. And we're going to expand from the number of spin flips. Okay. So we write the partition function as e to the minus E0 kVt, which is the partition function of the ground state. That's our reference state, and we only want to look at changes in response to the ground state. So that's the ground state partition function. And then I have correction terms 1 plus 1 equal 1 to infinity of different changes as a function of the lattice size and the order of the number of spin flips. And so this is now these are boards. Sorry, too big. These are Boltzmann vectors relative to the ground state. With n spins. And so we had this in when we looked at the discussed the heuristically the idea of the lower critical dimension in the Pyrus argument. And so we saw that each wrong bond results in or comes with an energy cost. So each wrong bond resulting from a spin flip increases the energy from the ground state by 2J. And so I have thus a Boltzmann weight with unsatisfied bond X is e to the minus j kVt, 2 kVgt. So I'm now looking at bonds. I'm not counting spins, but I'm saying like I'm flipping a spin. And what's the cost of this energy in terms of bonds? That's the change. High temperature series, we're enumerating spins. Low temperature series, we're enumerating bonds. Different. And then duality next week. And so if I have a bond not satisfied, it used to be at minus j, and I flip the bond and I go to plus j, so the energy cost is 2j. And so x equal, and now x is my expansion variable for the low temperature series. And so let me write this very boldly. So here we have bonds. And here we had we're looking at, this is looking at spins. Because we're here enumerating like the power of the spins, right? Oops, yeah. And here we're really counting the bonds. Okay. Okay, so and again, now we go to the square lattice and we think about like, okay, so how many bonds can I, if I have a single spin flip, how many bonds does this cost me? And so what's then the energetic cost in terms of X? And X is the cost for one bond. So on a 2D lattice, think of a single spin flip. Plus, minus, plus. So this affects 1, 2, 3, 4 bonds, right? So this, the Boltzmann weight is x to the power 4. And again, I need to enumerate of like how many different permutations can I have for, flipping a single spin. Well, if I have n lattice sides, I have I can do n times. Okay. Then how about 2 spin flips? Well, now again, these 2 spins, they can be in principle they can be separated like 2 independent spin flips, like in this configuration. And then I break 1, 2, 3, 4, 5, 6, 7, 8 bonds, right? So here my Boltzmann weight is x to the 8. And having 2 independent ones, I can have n times n minus 2, 5, sorry, n2 minus 5 over 2 times. Or I can flip 2 spins that are actually neighboring. Or I can have plus, minus, plus. And then I break 1, 2, 3, 4, 5, 6 bonds. So then this is x to 6. And And we kind of already see what this means. Like, you know, what's the power? What's important is the power of this of the bonds, right? Then flipping, and this exponent is kind of given by the boundary of the spin flips, right? So this measures the boundary of spin flip droplets. And as before, higher orders, complexity goes up quick. But let me show you 3 spin flips. So now I'm just drawing the minuses, how they can be, like the flipped ones, how they can be configured, right? So I can have them all next to each other, and I would have 1, 2, 3, 4, 5, 6, 7, 8, right? That's x to the 8. Or I can have them 1, 2, 3. Then that's 1, 2, 3, 4, 5, 6, 7, 8. That's another x to the 8 term. And this one I have 2n times. This is 4n. I can have 2 together and 1 separate. Then I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10. I can have all 3 of them like disconnected. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if I look at the permutations, then this is 2n and minus 8. And this is, oh gosh, n times n squared minus 15n plus 62 over 6. I'm here trusting humans, obviously. And you see, look, you know, here you're actually, you kind of, like it's on the horizon that we're running into problems, because we see that the n go up, the factors of n, but they will eventually cancel out again, right? So, but that's a check that we did everything correctly. I mean, just to mention, like if for 4 spin flips, I get terms that go up to x to the 16th, and for 5 spin flips, we even go up to x to the 20 already. So it really goes up dramatically. But let's have just a look at the higher order. And so at the lower orders for now. So what we now need to do, if we want to enumerate our partition function, go back to the front. So what it says is like, okay, so we have our ground state partition function, and then we're just going to sum over the individual weights in terms of x, and the amount of possibilities that we can have to enumerate the perturbations as we in higher and higher order in x. And so the tricky thing, though, is that this is not necessarily, so the order in x does not map to the number of spin flips, right? So for a single spin flip, I can get an for a 2 spin flip, I can get an x to the 8 term, and for 3 spin flips, I can also get an x to the 8 term. So you have to be careful when using this method to actually check for the higher order terms, because they might, the higher order number of spin flips, because they might contribute a lower order and x contribution to the partition function. And so the partition. Is then n x to the 4 2nx to the 6, and then summing over all the different x to the 8. It's half n plus 9. And so that was the caution note. Number of spin flips is not equivalent. X. So also higher number of spin flips contribute to lower order in X. Okay. The example being, for example, 4 spins flips contributes to x to the 8 already as well by 1, 2, 3, 4, right? So there we also have just 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have to be careful about that. Okay, so before we actually apply these decision functions and evaluate them specifically for the Ising model, I would like to generalize this result for a hypercubic lattice. So like going to a lattice in d dimensions and seeing how the dimensions actually play out here. So we can want to generalize to a d-dimensional cubic lattice. And so if I define the ground state E naught as that's just n dj, right? D for the amount of bonds that I have per spin. And there's a degeneracy of 2 for all pointing up or all down, right? So that's the ground state. So I can then write my partition function as 2e to the power of n d beta j. And now my correction terms here, I'm just going to rescale this exponent now with the dimension that's playing a role. So instead of if I have a single spin flip and I'm in 2 dimensions, it's 4 sorry. Sorry, I'm a little lost on how the D is defined. Didn't strike me. I will look it up. This is from Carter. But let me just go with this. Because we've been working in 4D, and D is 2, so this should be a D over 2 in my definition. Okay, I will look up how D is defined here. DNE. No, this is just change of notation, and I screwed up on that one. Okay, all good. Okay. So here. Okay, So what we do here is we have the amount of unsatisfied bonds. For the two-dimensional Ising model, we defined in this expansion variable x. But we can also just look at how does this cost j depend on the dimensions and how many bonds do I change. So I'm replacing this x by something where I'm enumerating the amount of bonds that I change when I go up in dimension. So it's n to the e 4d Sorry, my notes are inconsistent and it didn't struck me yesterday. I'm sorry. Okay, I will look it up. It's Carter. I'm switching from notations from Neumann's to Carter, and something is off there. Note switch in notation. Neumann's. I'll look it up. But the idea that you should take here is often obviously not knowing the exact terms, because who cares? But the idea that you can actually also generalize this this result of enumerating the bonds to any d dimensions, and also for these d dimensions calculate the free energy per spin. Which is mine is better. So I'm looking at this. That's then ln z over n. And then we get d beta j plus 1 over n ln 1 plus nx 4d dn x 4 2d minus 1. And so on. And this, again, as we did for the high temperature series, we here also expand for x small to get a more closed expression and to check that these higher order terms n squared actually cancel out. And this is indeed true. It has to be true. Minus 4. Minus 1. Okay. And so that's important because we expect the free energy to be independent of the number of spins within the lattice. So note again. And dropped out. Again. Very nice. And again, this can be used as a rule to generate rules of for enumerating these graphs. Two rules. And so now we can actually, look at thermodynamic variables, like, for example, the energy per spin side. That would be E over N, and that's then the beta of ln Z over N. And And this is straightforward to it. So hopefully this is where I get the notation with dx b beta is dd beta of e minus beta j minus j e minus beta j is minus jx. So using this, we're now taking the derivatives of dd beta of these x terms. We get a j contribution from the ground state, and then d minus 4d and we can also calculate the heat capacity. For example, CNKB, which is defined by the temperature derivative of the energy per site. So we can now really start learning about potential critical behavior. And so evaluating that, we get to, obviously, again, an expansion in terms of these x's. Okay. So obviously we don't care. Yeah.
Yeah, I have a question about the canceling of the higher order n terms.
Yeah.
So if I really want to like prove that or see for myself, would I need to just expand the ln in the small x and then sort after powers, and then through some miracle all the coefficients actually cancel?
Yeah.
Okay, so there's no trick involved. It's just really just calculate.
Yeah, it's just that the enumeration, like the when you do the permutations of these generated, like how different times you can have this, like when you just correctly estimate these permutations, then miraculously the terms cancel out.
Okay.
So which is more really like a check of like how did I do my enumeration correctly? Because physically it has to be that way, right? So I hope that's clear, right? So the free energy per spin can't depend on the size of the letters, and indeed it is, it's. I mean, we're still calculating physics, right? So we're calculating a physical model, so we don't. There's no way we can change the physics, so it has to come out. But I agree that it's kind of miraculously that if I really correctly enumerate all the different ways of how I can flip spins here, then all the terms exactly cancel out.
Okay.
But so I did a few of these expansions myself on a Mathematica sheet, just to make sure that these limits, where is it actually taking x to expanding for x small and these kind of things, if that's really true. But I'm not sure if it's like really insightful to understand physics. Like this is more math, and you should learn physics. And so here's actually where the physics starts again. So we're happy, right? So we can calculate. So we know the ground state, right? And we now have found a method of how we can enumerate deviations from the ground state, right? So we can calculate the free energy, and from the free energy we can actually calculate our thermodynamic variables that tell us about critical behavior. And so the one that I picked here is the heat capacity, right? So we would expect like a critical behavior of the heat capacity as the temperature approaches a critical temperature. And now the question is like, okay, so we can obviously, knowing the free energy, we find, I don't care how this equation looks, but the one thing to spot is that obviously I can go up in higher orders in X as I include higher and higher terms. Can this, going to higher and higher terms, can this teach me about potential critical behavior? And so, yes, it can, because I can think about expanding the heat capacity as it approaches criticality. I can also expand that as a series, right? And so I can actually compare the change of prefactors in this series as I include for higher and higher order terms to make an estimate about the critical behavior. So that's the idea that I want to show you. As I said, like, I don't really care. What you should take here is that we can, right? So we can do these calculations, and it looks very tedious, and I have no intention of you doing this in big detail. But the essence is, I can, if I really want to, I can go up to higher and higher order. And the question is, can now such a series be used to extract the critical coupling, say, coupling at which I expect criticality. I'm going to derive this. I'm going to give it away right now. It's beta J, seen for mean field also. And the singularities associated with a disordering transition. And so, okay, let's check. So say we found a series expansion of the heat capacity. And instead of writing down all these neat terms and the orders, I don't care. Let me just abbreviate it for the idea of the concept. I'm summing over a number of terms, and I have some prefactors, and I have some expansion variable, u of L. And now from the expected divergence, of the heat capacity, we expect, so physically you expect some prefactor and then a minus u over uc to the power of minus alpha, where right now I'm treating u as an expansion variable, but we're thinking about the temperature here, right? P over critical temperature. And so what I can now do is like, okay, so I expect this functional form, but I can also expand this functional form in a series, right? Okay, let's do that. So I can write this also as a series where I would have terms of alpha ucu plus c squared u L. Wait, that's not the L one, sorry. And I can even write down a general fashion how the nth term of this expansion would look like, namely alpha times alpha plus 1 times alpha plus L minus 1. Okay, so the else term, else faculty uc to the power of L, u to the power of L. And with some parameters A, U, C. And so now we expect that this expansion like these coefficients, they should actually match this coefficients that I get from this high temperature series expansion, right? So we're approaching criticality, and so like how we approach criticality, like the expansions should match. So we expect and so what we can do is like we can consider the ratio of consecutive orders, consecutive orders. So that would be if we have in our low temperature series expansion, we consider terms that we get for AL and relative to AL minus 1, AL minus 1, and we compare this ratio now to this expected behavior, and we look at the ratio of two subsequent terms. Why ratio? Well, because I get rid of all these factors. And so what only matters is that the alpha term has this extra factor more, here one more term and here factor L than the L minus 1 term. So this ratio from our expected behavior is alpha plus L minus 1 over L UC. This I can rearrange as 1 over UC, 1 plus alpha minus 1 over L. And so this suggests the following graphical solution, that if I were to plot AL over AL minus 1 in my expansion over 1 over L, then I would have as a y-axis cut off 1 over UC, and the slope of this curve should be alpha minus 1 over UC. So now what you can imagine that is that, okay, so I'm very patient scientist, and I keep going to higher and higher orders. Maybe, maybe I just have a really cool idea of how I can nicely find rules to enumerate all these graphs, right? And all these bonds, whatever. And I can go up to higher and higher order. And then I will just always plot this ratio of the higher order terms, the ratio of the subsequent terms that I find, versus 1 over L. And I kind of hope that I see my data sort of approaching a slope. And then if I can fit a straight line to the slope, I find both my critical parameter as well as my critical exponent. And this is indeed what people did. It does work. And so, oh God, water timing. And just to mention, so indeed, a generalization of this low temperature expansion to any discrete spin lattice models is also possible. Okay, so for today we found we looked at the two different regimes of how I can go from knowing my high temperature behavior and expanding, going down in temperature, and we looked at knowing my ground state and going up in temperature, how I can expand and look at have a series expansion, include higher and higher orders, and also how actually putting in this amount of work and looking at higher orders really can give me quantitative results about potential, critical behavior, and in fact, really allowing to quantify the experiments. Next week, we're gonna really apply it to the one-dimensional Ising model and compare the findings that we have then in actual terms with the ones that we had before, just to see that everything matches up. And then also ask the cool questions of like, okay, so I know something about this regime, I know about something about this regime. Is there a mapping so I can really learn about where they meet? And this is, I think, very wonderful physics that lies ahead. With that, I stop the recording and thank you for your attention.